Physics chapter 19 video 7 representing SHM graphically. So basically now we know everything about simple harmonic motion. So now we are going to represent this graphically. So there are three different kinds of graphs that we have to worry about in when talking about motion. One thing is, I hope you can remember them. One thing is velocity time graph. The other one is the acceleration time graph, and obviously the other one is displacement time graph. So here all three are happening. That is, there is a velocity and the velocity is changing. Why is the velocity changing? I'm sure you have guessed the answer. Velocity is changing numerically as well as because due to friction. This trolley, you have to look at this trolley. This trolley will reduce its speed after little by little. It will reduce its speed because of the friction. So this friction will basically basically reduce the speed. At the same time, because there is a change in the direction, that is, when the trolley comes to the extreme end, left or right, it changes its direction and comes back to the central point and goes past that, and again it goes like in a cycle. So this happens, then there is a change in velocity from 0 at the extreme ends. That is, at these 2 points, if these are the two extreme points that this would reach, from here it comes here and then goes back to this place, then at this point it would have a velocity of 0. At this point also it would have a 0 velocity, and at this point it would have the highest velocity, right? So that is something that you must know, right? This at the central point or the equilibrium position, it will have the highest velocity. So now acceleration is also changing. As you can see, acceleration is changing, velocity is changing. Then how does the displacement change? Right? Displacement is also changing because this is the central point with relevant to this. This becomes, let's say this is positive, then it goes back to this place which becomes negative. Positive, negative, positive, negative, that is the relationship. So the displacement is also being affected. Right? So these three graphs, how are we going to represent them in a graph is what we need to, what we are trying to figure out. And then first of all, we need to take accurate measurements. So this measurement is actually done by using a sonar technology. That is, there is a motion sensor. The sonar means related to sound. Right? So the sound, you can, you obviously, if you make something move from, left to right, right, you will hear the sound moving away and coming towards you. For example, I hope you can hear that sound, right? It is different from this sound, right? You can hear that, right? One continuous sound against this sound, right? So as you can hear, there is a difference in the sound. So that is actually a characteristic of simple harmonic motion. But if it is moving through like a pendulum swinging, it would not make sounds. But here we are talking about a trolley, it would have a characteristic sound. So now this motion sensor will allow us to record how the movement changes with sound. So there is ultrasonic pulses which can be detected by the sensor, and that sensor will give us a graph like this, right? So in this computer monitor, it will show us, and this monitor is actually giving us the displacement time graph here. We can actually vary and obtain a velocity time graph and also acceleration time graph. So here it shows the acceleration time graph, velocity time graph, and the displacement time graph of a particular movement, right? So as you can see, in the first one, it is the it is always x-axis is always time, which means we have measured the period. right? So the velocity and velocity, displacement and acceleration, they all have the same type of curve. This is mathematically, right? This is known as a sinusoidal curve, right? Because it is a sine curve, right? So these kind of curves are known as sinusoidal curves. I hope you understood. Then now let's try to figure out how this displacement time graph, that is the first one here, we are discussing this first one, right? How is that important, right? Let's try to figure out how that is important and what kind of information it would give. The displacement of the oscillating mass varies according to the smooth curve shown in figure 19.15a, right? So the top graph. Mathematically, this is a sine curve. Its variation is described as sinusoidal. Note that this graph allows us to determine the amplitude xo and the period t of the oscillation. So obviously amplitude is the highest point or the highest displacement. Because this is a displacement time graph, we can take this height, right? This height as the highest movement possible. Yeah. So highest possible movement, that gives us the amplitude, and also the period from corresponding peak to the next corresponding peak would be the period we can figure out, that is the time for a single oscillation. We can take those values. In this graph, the displacement x of the oscillation is shown as 0 at the start, right? We have measured from 0, that means it is in equilibrium position, right? Starting from equilibrium position only, we have started measuring, right? We have chosen to consider the motion to start when the mass is at the midpoint of its oscillation, but without pulling it to the left or right, it would not actually go into SHM. But we have taken to measure it starting from there, right? We can choose any other point, but it is easier and it is conventional for us to measure from there. I hope you understood all the details and explanation of the displacement time graph. Then the velocity time graph, which is the second one. The velocity v of the oscillator at any time can be determined from the gradient of the displacement time graph. You obviously know that the gradient time graphs, that is the first one, the gradient of a dt graph, displacement time graph, will give us the velocity. Right? So v equals delta x divided by delta t, change in displacement divided by change in time. Again, this will result a smooth curve, which is a sinusoidal curvature. It is just like the velocity displacement time graph, but in here it is going to start at a different point. Why? Because at the central point, that is, when this object is moving at this central point, it would have the highest velocity at the middle, right? I hope you can remember that part. It would have the highest velocity at the middle, therefore it should start at the highest point. Yeah, it should start at the highest point, right? So having that cleared, it starts at a different point. When time t equals 0, the mass is at the equilibrium position, and this is where it is moving fastest. Hence the velocity has its maximum value at this point. Its value is positive because at time t equals 0, it is moving towards the right. So right is positive. That is what we take. Then acceleration time at graph. Then we come to the acceleration of the oscillator, right? So this graph, right? At this, obviously at this point, it is moving at the fastest level at the central point, and it does not accelerate, it does not decelerate After that only it begins to decelerate. When it is going to the right, passing the central point, it has the highest velocity, then it reduces the speed or the velocity when it goes to the right. So that means passing that point, at the central point there is a velocity of acceleration of 0 meters per second squared. Then going to the right, it increases the deceleration increases. As a result, it would have a negative value because it is decelerating, right? Then at any point the acceleration can be taken by the gradient of the vt graph or the velocity time graph. A equals delta v over delta t. So this is actually basic mathematics and physics that you have learnt in your O levels. This gives a third curve of the same general form, sinusoidal curvature, which shows how the acceleration A depends on time t. At the start of the oscillation, the mass is at its equilibrium position, no resultant force acting on it. Therefore, as a result, because there is no resultant force, there is no acceleration. You can go either way. There is no acceleration, therefore there is no resultant force, right? So that is also something that you must understand. As it moves to the right, there is a, what is the force that comes into effect here? The restoring force. Because there is a restoring force, that restoring force will actually create in a deceleration. Where is the restoring force is acting in which direction? It is acting now when it is going past this point. It goes past this point, but the restoring force is acting towards the equilibrium position. Because it is acting against the movement, it would have a negative acceleration, or rather a deceleration. As it moves to the right, the restoring force acts towards the left, giving it a negative acceleration. The acceleration has its greatest value when the mass is displaced farthest from the equilibrium position. Notice that the acceleration graph is upside down compared with the displacement graph. This shows that acceleration is directly proportional to the negative displacement, right? So you can see here, it is the upside down version of this and this, right? They are quite equal. Not the values, but the times would be the same, but it is the upside version of this thing. Acceleration and the displacement are not equal, the values of acceleration and displacement, but the graph would have a similar point. So acceleration is directly proportional to the negative displacement, or A equals you can take it as A equals K negative X. In other words, whenever the mass has a positive displacement, its acceleration is to the left and vice versa, right? So when mass has a positive displacement, that means to the right. Acceleration is to the left, that means it would have a negative acceleration. It is decelerating, right? When it have a negative displacement, it is acceleration is to the right, etc. That is how it moves, right? Then we will discuss this part as well before we move on to we will write the note and then come back to frequency. Write down the note. Representing SHM graphically. When a trolley tethered between springs is pulled to one side, it will continue to move in simple harmonic motion. It will continue to move in simple harmonic motion and the variation of its movement can be understood by listening to the sound it makes when going back and forth. When going back and forth. Using a motion sensor, this can be better detected and relevant dt, that is displacement time, comma, vt, that is velocity time, and at, acceleration time, graphs can be obtained. Pause the video and draw these three figures, the three graphs, and under that write down displacement time graph, the displacement varies as a smooth curve within brackets sine curve or sinusoidal curve. It is conventional to start when the displacement is zero, that is at the equilibrium point. It is a smooth curve because the velocity changes as a result of the restoring force. That means because there is a restoring force, it will result in a acceleration or a deceleration. That changes the velocity. Because the velocity is changing, this becomes, it is not a straight line. Then write down VT graph. Velocity can be obtained by finding the gradient of the displacement time graph. V equals delta x divided by delta t. This will also have a smooth sinusoidal curve. However, as the velocity is at its highest point, when the object in SHM is passing the equilibrium point, it would start as shown above, that is at the highest point. I hope you understand. I hope you listen to these details properly and understand. I hope it is not a waste of time. Then acceleration time graph. Listen carefully and understand, and also please raise questions if you have any questions. Acceleration can be obtained by finding the gradient of the Vt graph. Write down A equals delta V upon delta T. This would provide the upside down sinusoidal curve of the displacement time graph. At equilibrium position, there is no restoring force. There is no restoring force. As a result, the acceleration is zero. Going to the right, it has a positive displacement, but as the restoring force is towards the equilibrium position, it would have a negative acceleration. At the farthest point, acceleration would have its greatest value. This provides the following relationship, and then write down this relationship. Acceleration is proportional to negative displacement, or A is proportional to minus x. And also write this statement as it is. In other words, whenever the mass has a positive displacement within brackets to the right, its acceleration is to the left and vice versa. I hope you understood the explanation, and I hope you have a thorough idea about how SHM can be represented graphically and what kind of details can be obtained through these by referring to these graphs. If you have any questions, please ask. If you don't have questions, please go to question number 7, 8, 9 and 10.